Okay, so we're here with Arun Kishan.
Yeah, Kishan. Yeah.
Kishan. And tell us about yourself. You're a developer down in hardcore Windows world. What are you working on?
Yeah, so I own basically the process management and threading subsystem in Windows, as well as the debugging support. We have a kernel mode interface to that, and various other miscellaneous things, but primarily the process management stuff.
Cool. So how does process management work in a general purpose operating system? I mean, that's a complex problem, right?
Sure. There's many aspects to it. I guess process management interacts with other components that you've already covered, like object manager, memory manager, and the scheduler also. So, kind of at what level detail do you want to discuss?
Well, let's keep it up at the higher level for now, and then we can dig in as you'd like to.
Okay, so basically, the process management subsystem provides the set of APIs that you can use to create processes, threads, query information about them, change properties on them, terminate them, open other processes, create them under certain user contexts, like I want to, run as, for example, that kind of stuff. It doesn't deal too much with actual scheduling, for example. That is provided by the scheduler component. We just, provide interfaces to create these and manage these things. There's a layered design to the kernel, and the way it works is, I can
go for it. Love the way it's worked.
So, if you look at the kernel, we have what's called the KE, the core kernel component, and then we have other kernel components. Put memory management here because this is a component that KE kind of talks to directly. And then we have other things like process management, thread management, security, so on. And for the most part, code inside KE is pretty self-contained. It doesn't really deal with these upper levels. You would consider these to be the executive layer in the operating system.
Because they deal with execution.
Well, this is kind of a formal term that we have. So for example, we have a data structure which we would call the K thread object, which is the kernel thread, and what this would have is state relating the machine state of the thread as well as like priorities and stuff. So this is just the information that the scheduler needs to figure out which processor this thread should run on, and other machine state of the thread, right? Priority, whatever. Now, the process management layer sits on top of this and exports an object called the E thread. This is an object manager object, right? Which basically is a container for the K thread object, and it now includes lots of other stuff like, the impersonation token, various synchronization stuff, and so on. It's kind of the interfaces to these other components. And this is what provides all the system interfaces that user mode apps can call to create threads or whatever. Even for drivers, we provide a set of interfaces to do thread creation and so on.
Excellent.
So
that's pretty much what you're doing as process manager.
Yeah, this specific component's like kind of the big area I own. There's a whole bunch of user mode code that creates like a meta layer on top of this that I also work on quite a bit.
So that's for the Win32 people to program against.
So the original design of NT, going back to here, was to be very general purpose. So you had kind of your kernel, now including everything in the previous diagram, and then user mode, and we have a what's called the system DLL, which is NTDLL, and this provides all the native functionality, the NTXXX form of APIs, and the processes and threads you create through these interfaces found in NTDLL are what are called the native threads and processes, right?
Sure.
And separate from that is Win32. Like today we don't think of this difference, but initially when the system was designed, Win32 was a separate subsystem. NT was designed to allow different subsystems to run on top of it. Win32 was just one of them. Another one was POSIX. And another one was OS2. And the idea was that each of these would provide some library which would provide a way to create threads or processes, which then went through NTDLL into the kernel. And there was a separate process, like a subsystem privilege process for each of these subsystems that would, manage specific semantics for that particular type of process. So today we still have CSRSS, which is the Windows subsystem process. And you see this, if you look in Task Manager, and it's running in each session. What it does is it basically is the server side. There's one instance of this for all Win32 processes. So it manages all the state about, Win32 processes. And the POSIX has a similar one called POSIX. If you install software services for Unix, which Microsoft supports, then you'll see this subsystem. And this subsystem provides like the POSIX APIs for like fork, whatever. And it's built on top of the primitives that NT provides. And then OS2 is no longer supported, but this is kind of the basic model that we provide. And so the API that most people are familiar with, create thread, create process, create process as user, all these different variants are implemented in DLLs, client DLLs that you would load into a Win32 process, kernel 32 or advapi, which then will do some processing on these arguments, let CSRSS know about this process that we've created, and the process or thread is created through native interface, but that's not exposed to apps. And then you'll notify the CSRSS or whatever that this thing has been created, so these subsystem processes can maintain some state about them.
Excellent.
So that's kind of the original design. Today, primarily, we just have this.
Just Win32.
Right.
Yeah.
And this is an optional component.
Sure.
But the original design of NT allowed this. And specifically, if you look at your process object, the E process, which is kind of like we talked about K thread and E thread, this is a executive process which contains a K process object. And the K process is the object with like affinity and priorities and quantums and that kind of stuff that the scheduler cares about, as well as some low-level hardware stuff like the page table base, right? Like kind of machine-specific stuff. At the E process level, it's more higher-level constructs. So we have stuff like token, various ports, like a debugger port, if process is being debugged, and what's called an exception port. And the exception port was added so that when you take an exception, first it goes to the debugger if there is one. If there isn't a debugger, we go back to user mode and try to run the exception handlers. Right? When you do your try finallys, this is where you get a chance, you take a AV or whatever.
Sure.
If that's not handled, we have basically a global handler that sits at the top of all threads. I mean, we can talk about that in a little bit.
We should.
And what that does is it basically says it can't handle the thing. And if that's the case, it'll go back to kernel as a second chance. And in that case, it'll go to the debugger again. This is where sometimes when you're debugging, you'll see AV second chance. So that's what it is. It's like it wasn't handled by any exception handlers. If that gets ignored, then it goes to this exception port. The exception port is usually implemented by one of these guys. So CSRSS doesn't really do anything except blow away the process. But POSIX attaches an exception port to each of its processes that it knows about. And this lets POSIX do things like, provide signals. For example, an exception. When you take an AV, it's supposed to be like a sig-sev, right, in the Unix world. And that's how they do it. Because they've hooked up an exception port to the processes they know about.
Excellent.
So that's kind of like a high level of what's going on here.
Very interesting. So, in essence, so an e-process is a wrapper for, so you extend kernel process. Is that a way to think about it?
And the e-process and e-thread are actually object manager objects, which we've covered before.
Sure.
Whereas at the kernel level, kernel really, except for very exceptional cases, doesn't deal with OB level, right? It's underneath OB, so it doesn't deal with referencing objects or dereferencing objects or any of that. But e-process is an object manager object. So what we do is we'll create an object manager object, e-process, initialize the k-process portion using the ke functionality, then fill in the rest, and then that gets exported to user mode via handle. This is your process object.
Cool. So what you're saying then is an object is a user mode construct. The kernel doesn't care about objects.
Well, when I say kernel, I meant specifically the core kernel piece, which is this KE. The rest of the kernel does use objects, like Adrian talked about, referencing objects, dereferencing objects, whatever. But at this level, the K process, right? So theoretically, you could have objects or data structures that are just K process without a containing E process that was an object, right? If it was only manipulated at this level.
Understood.
Right. But in all intensive purposes, all threads and processes end up being e-processes and e-threads because they end up needing to interact with these other components, which treat them in those ways and use the APIs that the PS level provides. The PS only deals with e-processes and e-threads.
So are there threads that go on that only happen inside the core kernel? Like, are there things that the core kernel is doing where it requires threading? Or is that really just necessary for the rest of the world?
So, when I say core kernel, it's still in the kernel address space, right?
Got it.
What it is it's just a module. It's a separate part of the kernel that does specific things. It's kind of at the very lowest level. If we have a layer design for the
it's closest
kernel,
to the hardware,
right?
Okay.
Effectively, and under this is what's called the HAL.
Oh yes.
But this is kind of the lowest level. This is where you'll see like most of your platform-specific code. The only other kernel component that has as much platform-specific code is going to be probably memory management, right?
Okay.
Because it also needs to know about the hardware and how to do paging and all this stuff.
Certainly.
Process management has some knowledge of hardware-specific stuff because we're managing context for threads, right? What registers go and where do we put the argument when you create a thread, and so we need to know which registers to stick stuff in. So we have some knowledge of it, but most of all that is at the KE level. So there are some things that are started as basically static, K process or K threads, and that's basically like when we boot up. For example, we bootstrap everything in, and so the first K process is part of a statically defined structure, which ends up being the idle process.
That's what the idle process is, huh?
Yes. So the idle process, when we start up, we're just running code, right? And so what we want to do is eventually bootstrap the system. So we have this structure which we set to equal the current process. This idle process, we initialize it, and then for each processor in the system, we create a idle thread. So the idle thread is really a thread at the KE level, right? That really doesn't get exported out. It's like a defined global, or for subsequent processors, it's dynamically allocated. But conceptually, it just runs the idle loop. So the scheduler picks this thread to run, and there's one per processor. It picks it to run when there's nothing else to run, right? And so this thing is kind of the one process that's purely kind of really at the KE level, right? PS doesn't really know about it for the most part.
And so, could you just briefly describe, like, what is the purpose of doing it that way?
It's just a bootstrap thing that we have, because when we start up the system, we don't really have processes or threads. So we have the statically defined structure which we initialize as the first thing, and then we have to call into initialize process management, right? And so the real first process that's created, first real process, is the system process, which I'm sure you've seen also.
Sure.
this thing is ID 4, which is actually the first real ID. If you look in Task Manager, you'll see idle processes ID 0. That's all like we just present that image to make it consistent. It's not a real process in that sense. The first process that gets created by process management is system process, with the idle process basically as the parent, right? And so this thing starts up, and we create all the system threads to run inside the system process.
Interesting.
And these threads run purely in kernel mode.
Okay.
Right? They're like helpers for both the system and drivers can create these things.
Very cool. So how do you go about managing this stuff? So you're managing processes and threads.
Okay.
That's what your component does, right?
Right.
So I'm a programmer in Win32, and I say, or even in managed code, forget about Win32 for now, because it's the same thing in the end,
Sure.
right? So I say, new thread.
Mm-hmm.
I just in my code, right? New thread.
Sure.
So
what happens?
What happens?
Okay.
What are you doing? How does it work?
So, okay, let's step back from all this.
Sure.
This maybe went a little deeper than...
No, deeper is good. Well, it's good to understand the context. And we've seen those diagrams before.
Okay. So, let's just talk about specifically what is a create thread.
Yep.
Okay. So to create a thread, there's two classes. There's system threads, which run purely in kernel mode. So we're not interested in that. We're talking about user mode level, user threads. So to create a user thread, what we need is basically we need to know process that it's going to run in.
Yep.
So you can, in NT, you can create a thread in your current process, or we have interfaces to do create remote thread, which is create a thread in the other guy's process, right? As long as you have access to open the process for the appropriate privilege, you can do this.
Sure.
So you need to do this, you need to have a stack to run on, and you need like a context, basically. And this is pretty much it. We also have this idea of a tab, which is a thread environment block, which is associated with every thread and has some info that threads can easily access. We usually set a register to point to this thing, 32-bit, for example, with FS, and it provides a way to find, like, for example, thread local storage or whatever in the context of that thread. So this is kind of the stuff we need to, like, create a thread. So when you say create thread, we'll come into some DLL for convenience. Let's take the Win32 stuff, so kernel 32. And then we'll basically call, the NT service, NT create, thread. And there's like a EX version in Vista. So there's a multi-step process here that occurred previous to Vista, but conceptually it's all the same. What we'll do is we look at some properties that they've specified about what kind of stack size they want. And the stack has two elements, which is kind of the virtual size of the entire thing, which is called the reserve, basically. And then there's the committed portion, which is the part that's actually backed to page file at any time. And what we do is we can grow on demand, because we have a guard page at the end. I know if Landy talked a little bit about this in the memory management section, but what we do is this allows us to then grow as we need and not actually commit the entire thing.
Excellent.
So the user can specify what they want here for both the reserve and the commit. And then we take basically the start address that they say, because when you create a thread, you have some code you want to run. So you give us a start address and you give us a parameter. And we package this up into a machine context for your platform. So if you take x86, you'd have your EIP, pointing. You want it ultimately to point to this, and some register or on the stack this parameter be present, right? But we have to do a little bit of magic to actually get all this to work. When you pass this in to the kernel, what we want to do is we want to first run our code before this thread starts up, and we want to put some wrapper around the actual start address. So without getting into a lot of the nitty-gritty mechanics, conceptually, what happens is we take the context that describes, we take these things, and what we do is we actually have a wrapper function in NTDLL we're talking about Vista now. This is not quite this way in older OSs, but conceptually it's the same.
Okay.
It's called like the RTL user thread start, which is kind of like a wrapper base function that all threads start execution at.
Okay.
And we know where this address is because the system during boot maps the NTDLL and looks up some key entry points. So we know where this function is. What we do is we construct a context that says, hey, let's run at this address, and we pass it 2 arguments, effectively.
Okay.
Those 2 arguments are the user start address and the user parameter. And we build a context that describes this,
Okay.
right? So the instruction pointer is going to be here, and we have these in the arguments. And this is like, let's call it context A. Now what happens is, before the thread actually runs, we want to bootstrap some stuff. There's some user mode state, that we want to have set up before the thread starts running user specified code. So what the kernel actually does is we change the context that runs to run a special piece of code called the loader initialization. So loader initialization is a bunch of code that's in NTDLL, again, that either initializes the process for the very first thread that runs in a process. It'll run some special code that creates the heap, sets up a whole bunch of data structures in NTDLL, like the library database, like which libraries you're loading. And for every subsequent thread, it allocates some thread-specific state, and then basically calls each of the DLLs with a thread attach, saying, hey, there's a new thread in the process. And we want to do that before we run the thread's code. So what we do is we actually change this context to a set context that, the initialization context, the init context. And what we do is we take this context that the user really wants to run, we plop it down on the user stack. So this is the user stack now. And you effectively will plop down this user context here. And we'll actually have the real context be this init context, right? And the init context has as one of its arguments, has this as the instruction pointer, the loader initialization. And one of the arguments is going to be this context. It sounds a little confusing. What happens is when the thread runs, it'll run the loader initialization. Loader initialization decides, is this the first thread in the process? If it is, then let's initialize all the process data structures, create the heap, etc. If it's not the first thread, then it'll run the thread initialization. And then what it does is executes a special system call that says nt continue, which you can think of as basically change my context to be what I'm passing in. And what we'll pass in is this pointer to this thing, which we copied to the user stack earlier. And basically it'll effectively change the processor state to be running at what's specified here, right? And then we start running the user code, but not quite. Because as I said earlier, we always wrap it with this RTL user thread start.
Okay.
So what that thing does is RTL user thread start basically has a try, except, here is where it calls the user start address and passing the parameter. This is like the OS function, but what we've managed to do is by always running in our code, we're able to put a try except around the thing.
Okay.
And in here, what we do is we call the unhandled exception filter, which we have a default one, but can be set by an app. You can say set unhandled exception filter.
Cool.
There's 2 levels of that. Kernel 32 sets the one that NTDLL knows about. That's not like a publicly available interface, right? That's like what the subsystem module, which in this case is going to be the Win32 processor, will be kernel 32. It'll fill that in, and it'll point to kernel 32's unhandled exception filter. Kernel 32 exports another API that let apps specify a helper function that this thing calls, right? So there's like a 2-level step here. What I'm talking about is at the OS level, the NT level, We only care about the filter that kernel 32 provides, not the user-specified ones. Kernel 32 manages that once we call them.
Sure.
So this thing implements all your error reporting and all this stuff and crash, because this is the last exception handler on your stack, right? It's at the very top. And basically, if this thing doesn't handle it, it'll unwind, go to the kernel, and do that second chance stuff we were talking about.
Mm-hmm.
Otherwise, it comes in here and it basically terminates the process. That's what we do in this handler, effectively. On the assumption that if you took like some corruption,
Okay.
right, we don't necessarily want to keep running.
Absolutely.
Right, we don't want to just terminate this thread, we want to probably blow away the whole thing, which is why what...
Well, that's an important point
Yeah.
that you just said. I mean, to stress that, you terminate the process even though it's a problem inside the thread.
Right,
Okay.
and we made this change actually, I think relatively recently, just a couple releases ago. Before, we used to just terminate the thread, you know, on the second chance, even in the kernel, we would just blow away the thread, and then we thought, well, maybe we don't want to let this thing keep limping along with some corrupt state that causes crashes, becomes vulnerable.
Absolutely.
So what we did is we just blow away the whole thing now.
Interesting.
Yeah. So this is kind of like how when you create a thread till we actually get running, all this other stuff goes on.
So you call create thread, and then this cascade of operations happens.
Right, and then part of that is also, you know, actually creating the stack, and the stack is not anything really special.
Mhm.
It's just a allocate virtual memory call. And this thing allows you to specify both that reserve size I was talking about and the amount that you want committed. And then all we need to do is set the stack pointer in this context appropriately to point to that block of memory, right?
Okay.
As far as this OS is concerned, only thing that makes a stack is the fact that threads stack variables point to that blob of memory, right?
Interesting.
It's just a blob of memory otherwise.
Okay.
So this is how you create a thread.
Cool. Now, I mean, it's good to always talk about the difference between a thread and a process, right? So
Okay.
you're the process manager, which implicitly means you're also the thread manager.
Yes.
So if I create a process that has only one thread in it,
Mm-hmm.
that's fine.
Yes.
You can't just create a thread outside of a process.
Exactly. So as I was saying before, you need to associate a thread with a process, fundamentally, either the current one or a different one. System threads also are associated with a process. They can be associated with a user process,
Mm-hmm.
but typically they're associated with the system process, the very first process we create on the system.
Okay.
The only difference really is that they don't have any user state. So there's no user stack, there's no TEB, thread environment block, that we access from user mode.
Mm-hmm.
These things execute purely in kernel.
Okay.
And so one thing I didn't mention here is we have this user stack, but when you run in kernel, you need a kernel stack. Both of those things are created as part of creating a thread. And the kernel stack is much smaller than the user stack, but we basically set it up so that whenever a kernel or thread transitions to kernel, we auto switch execution to the kernel stack.
Interesting.
On interrupts also, like when you take a page fault, it's set up so that we begin execution in the kernel on the kernel stack.
Okay. Now, one of the things that happens once in a while inside of a process is that it becomes hung.
Yes.
So are you the construct that manages a hung process, and how do you figure out that a process is hanging?
Okay, so there's a whole bunch of things you can do to try to see why something is hung. One of the things that is done is, for example, to look at what threads are waiting on. If they're waiting on events, we try to correlate that with critical sections, which are, we have a list of those. So by correlating that, we can get some idea of what the deadlock is, right? Usually that's what a hang is, right? Threads waiting on something that's, not being signaled, or they're waiting on each other. They've created a cycle in what they're waiting on.
Sure.
So that can happen, but the process manager has to guarantee that if that happens in user mode, the process can be blown away, right? By an administrator at least, right? Or you need to be able to go into Task Manager and right-click and say get rid of it, right? Because as long as the process is there, it's tying up lots of resources. So we need to guarantee that no matter what happens, even if you get this frosted window on your desktop, if the hang is in user mode, we can blow this thing away. If the hang is in kernel, that's more likely to be a kernel issue, and it's harder to make that guarantee.
Sure.
Right? But from a security and reliability standpoint, the admin needs to always be able to blow these things away. And you need to always be able to blow away things in your context.
Mm-hmm.
So we make that guarantee. There's another team that actually specializes in this diagnosability stuff for hangs and what's causing them and which locks are involved.
Okay.
Specifically, we don't own that specific piece here.
Sure. But it lives in the process management
The
infrastructure.
diagnosability stuff?
Yeah.
No, it's separate. It's mostly an entirely user mode thing. It has some hooks to look at state in the kernel, but
Okay.
mostly it's a user mode thing.
Cool. So I guess but it's happening in real time, right?
The diagnosability or
Yeah,
why?
the diagnosability.
It happens when they think there is a hang,
Got
meaning
it.
there's some responsiveness lag for some time.
For some time, and the thread's there's no
Yeah.
communication, and it seems to
Yeah,
be
I don't know all the metrics they use to decide,
Sure.
hey, this thing is hung, but
Okay.
this is the basic idea.
Very cool. And so let's talk a little bit about what's new in Vista.
Okay.
I mean, you mentioned the new, call
Yeah.
you can make to create.
So, right.
So what else have you done for improvements in process management?
So there's a few things. So this EX thing that I was mentioning is more of an artifact of some other work we did.
Mm-hmm.
You mentioned briefly before that, you can't have a thread without a process.
Mm-hmm.
But in the original NT design, it wasn't true the other way. You could have a process and not have threads. You could just have an empty process. That wasn't exposed via the Win32 interface. You could just create process and it would, run some code.
Mm-hmm.
But the NT interface let you create, if I erase all this. So if you said create process. So this thing would basically follow a multi-step thing. First thing you would do is you do an NT create process, EX or something it was called. This creates an empty process container, and it takes as input a bunch of things, one of which is the image section object. So this is a memory management object that basically represents a particular file. This is what you want to execute, right?
Okay.
So we would create this thing first, then what we would do is we would create a thread in it, right? So the process could exist for some duration of time without any threads, right? And some people actually use this functionality to create just basically scrap address space, right? You can just use an empty process for that. Now at the Win32 level, that's not exposed, right? At the Win32 level, it does both of these under the cover, so you don't get one without the other.
Okay.
If you think about it, now you have a window here in which there is no thread in here, and we need to create a thread in there,
Okay.
right? And the thread needs a stack, and various other things we need to be able to write into the address space, for example. I mean, the key things you can think about is fundamentally we need at least these two access rights to the new process. We need to be able to write the VM, and we need to be able to create a thread. Right?
Yes.
Basically, in order to get something that's runnable.
Okay.
Now, you could probably guess that if I told you had these two rights to a given process object, you could pretty much do whatever you want, right? Forget the thread that we're going to create. You could create a remote thread using these two accesses, right, to basically run whatever code you want in there. This is called code injection.
Sure.
Right? So you could inject code, basically you could write a whole bunch of VM, fill it with instructions, then create a thread to run at that address, right? You're saying, well, why does this really matter? Well, we started looking at some scenarios in Vista where we want to be able to basically activate a process that once it's activated, you don't have any access to. It sounds kind of weird, but there are some cases where this is kind of interesting. And so the obvious one, of course, is media content protection, right? You start up one of these things, once it's running, even if you're an admin, right, you don't have any real right to go and poke in there and see what's going on, right? To try to steal the content.
I see.
So these are kind of software protected processes, right?
Okay.
And now an easy attack against this whole thing, if what we did is only at this level we strip the access rights out.
Mm-hmm.
And we prevented only after this point, after we created this thread, that you can't create a thread, you can't write VM, you can't do all these dangerous operations. There was that window in which a malicious or clever guy could inject code in there. Once you can inject code in there, you basically control the process.
Yep.
So we wanted to have a model where you kind of could activate kind of a privileged activation in some way. You say run this thing and it starts running, and once it starts running you can't do anything to it. Of course, unless you're in kernel mode, because kernel mode has full access to everything.
Absolutely.
So there's a variety of technologies in Vista that are aiming to enable this form of kind of privileged activation. Like, we didn't go all out where you can't, in Unix you have this idea of set UID, like an app that's marked this way and you run, it will run under the credentials of the owner of the file. And you could see there too, if I wanted to let you run my text editor as me for some reason, maybe that's not a good example, but just theoretically, once you run that program, I don't want you to be able to like inject whatever code you can into there, because then you could read all my private files, right? I want to kind of let you do just one operation. So text editor is a good example. Maybe something like on Unix, the password program is set UID, because it does a specific operation which is to write the password kind of into the password file, which is only accessible to admin. So the password program, I don't know if it is anymore, but at some time it was set UID, right? You would elevate to admin, do this operation, right? But in the meantime, you don't want to be able to take over the password program and do whatever you want as admin, right? So it's similar to that. We want to activate something. Once it's activated, it does a specific task that's been vouched for, and we don't want you to be able to interfere with it unless you're in kernel. But if you're in kernel, we have other gates there that's supposed to make it a little more difficult to get whatever you want to run in kernel, even as admin Vista. I'm sure you've heard of some of these technologies, but
absolutely.
I mean, it's not all airtight, but we're trying to get there eventually. Right now.
Absolutely.
And the first step here was to combine all of this stuff, at least the minimal shell of it, right? To have one system interface to say, create an executable unit. And an executable unit is going to be the process plus thread plus stuff needed to execute, right? Meaning the exe, stack, whatever, right? So we added a new, basically native interface that create process could use that could do this. And when you returned from this, you had only very limited access to this thing, unless you got into kernel. And so that was a big change we did to the entire model, but we've made it transparent to apps. All the apps today will use create process or create thread, and they will transparently be using this functionality. Only if you try to activate one of these special processes does the privilege change when you create it, meaning we'll restrict the access you can get. So, and you know, you might say, oh, this is kind of dangerous, because what if it's like a bad program and then I create it and now I can't do anything to it, right? So we allow you to do certain things. We allow you to terminate it. And another thing we do is we verify signatures on this thing to be some known good program. Only some known good file can be executed in this mode, right? If it's not signed in this way, you can't create one of these protected processes.
Understood.
Right. So you can think of as many attacks as you want to get around this stuff, but you know, it's like a first step.
Good.
That we did in Vista.
Excellent. So now, what about dealing with the notion of multiple processors and multi-cores? Like, what has that done for you in terms of, you know, what does that mean to the process manager that I'm running on a machine with 4 cores in it?
So today, process manager generally does not do anything with that realm, right?
Okay.
It's more in the realm of the scheduler, the affinity. Affinity, right? You're talking about which processors you want different threads to run on.
Exactly.
So we provide interfaces, right, that say set the affinity on this thing. But once we set the affinity, the KE, that bottom level, is the thing that looks at those and says, okay, where can I run this thread? So decisions on where to run threads and at what priority they run, that's at the scheduler level. It's kind of decoupled from all this.
Okay.
Right, in some way.
But you're communicating with it to some degree because you're managing the threads.
Right, we provide the APIs to set these things, but the actual where it goes or whatever is based on who's setting those affinities.
Okay.
Right, and the scheduler is aware of, you know, multi-core and multiple processors per core and hyper-threading and all this kind of stuff.
Mm-hmm.
But at our level, we don't necessarily care. We just let the inputs pass through and let the scheduler do what it wants with that.
Cool.
So,
And then so let's talk about what happens now when I say kill thread.
okay.
I mean, obviously you don't just blow everything away. What goes on, or do you? Do you
So-
like rewind? Or
So
like,
this may be very shocking to you, a lot of people, but actually we do really just blow it away right there.
Okay.
And it's a little more complicated than that, but not too much.
Okay.
So,
So I mean, the point is though, the programmers need to, before they call kill thread, make sure that what they're
right,
doing
I mean,
is ready to be
basically,
killed.
right, so, exactly.
Okay.
So good point. Since, I'll get to that in a second, when you call terminate thread, if it's executing in user mode at the time,
Mhm.
it's basically instantly killed. Meaning, if it's holding critical sections, locks, manipulating some data structure, whatever, all this stuff is left in whatever state it was in at that instant, right? So it's possible you could get hangs now because there's no owner for this critical section, right? We don't release critical sections for threads when we terminate them. So OS kernel level don't know what critical sections the thread owns.
Sure.
For example, it's pure user mode construct. And even if we knew about critical sections, we won't know about some homegrown block that you've written in your program.
Mhm.
So you're kind of left in this weird state. So you can never really use terminate thread, as you said, unless you know exactly what the thread is doing, what state it's in. Is it safe to kill? So really, the API is use at your own risk. Now the other side of this is the kernel mode. If you terminate a thread while it's in kernel mode, it's a little different.
Okay.
And there's two aspects to this. There's user mode threads and there's system threads. So let's talk about user threads first.
Mhm.
Let's say you made a system call and you're deep in the system, right?
Mhm.
Allocating virtual memory or whatever it is, and you get a terminate. The way a terminate is implemented on NT is basically via asynchronous procedure called APC. APC is basically a little block of memory that we queue to a thread, which basically interrupts the thread, right, and executes a special piece of code. Okay? And we use this for certain things throughout the system. One is terminate. Others are like IO completions and things like this. Basically where you want to run a piece of code in the context of a particular thread, and it's in the context of the process the thread is in, right?
Okay.
So when you're in kernel mode, we'll queue an APC to you. Or if you're in user mode, same thing. If you're in user mode, the interrupt is instantly taken because APCs run at basically what's called APC level. So I don't know if you're familiar with this, but there's this idea of interrupt request levels on the system.
Okay.
So user mode code all runs at passive, which is the lowest interrupt level. So any interrupt level higher will preempt it to run that piece of code.
I see.
So APC is level 1. DPC is deferred procedure call. It's used by drivers. After they do their interrupt service routine, they'll queue a deferred procedure call. This doesn't care what thread or whatever it runs on. It just wants to run at this interrupt priority level, which is 2. And then there's a whole bunch of device ones, and then up here, you have like clock timer and stuff like that.
Okay.
There's hardware interrupt ones. So the main thing to know is that all user mode code always runs at passive. APC is level 1, so if you're running in user mode, you'll instantly take this APC interrupt. Now it's a 2-step process. The first thing that we do is we requeue a user mode APC. Right? So this is a little confusing. A user mode APC is kind of not an APC in the sense that it interrupts people. It's an opt-in thing. You have to say, I am ready to take a user mode APC to have one delivered.
Okay.
And it will happen at the time that you're returning to user mode. it'll run this code instead.
Okay.
And the idea is we don't want to interrupt your code at any random point when you're not ready for it. Because let's say you're running inside some code, you take one of these APCs and you call back into your code, right? But you might have been holding some locks, so you'll deadlock on yourself. This was a classic problem with signals in Unix, right? So there was a design decision made early on in NT that these user mode APC calls will not interrupt arbitrary code. You'll have to say, I'm ready to take one at this time. Now, terminate's a special case because you're not going to be in a state where you're saying, I want to take one right now. So what you do is you'll queue a kernel mode APC, and once the kernel mode APC fires, it'll fire, at APC level. There's a little more mechanics in there, but conceptually it will fire. Then we will queue a user mode APC and force this I am ready thing on, right? So what happens is when the user mode thread's running, it'll take the APC interrupt. We'll queue a user mode APC that said I am, ready to take one. And before the thread returns back to user mode, it'll run this code. Now, user mode APC has a kernel part and a user mode part. This kernel mode part runs before we return back to user mode. And this is where we call exit thread in kernel. So it seems a little convoluted, but you'll see in a second why it needs to be this way.
Okay.
And the user mode part of this never runs, right? Because we run this part and this thing does the exit thread, which basically says, no, don't run me anymore. And then it queues the object for deferred dereference, right? Because you can't dereference yourself while you're still running because the memory will go out from underneath you. So it kind of swaps off, puts itself on a list, and it's asynchronously dereferenced.
Okay.
Object manager object, right? And then when the last dereference goes away, the whole thing gets deleted.
Okay.
So you're wondering, why is it this complicated? Well, it's this complicated because what if we're in kernel mode at the time you take one of these? You don't want to just blow it away right there. If we blew it away right there, let's say you're in a system call, you've allocated a bunch of memory in kernel, like non-paged memory, whatever, and we blew you away right there, all that stuff would be leaked, right? And that's like a serious problem because kernel resources are shared amongst everyone on the system.
Sure.
So if you could just create a whole bunch of threads and blow them away when they're in the kernel and leak a whole bunch of state, the machine would be unusable, right?
Yeah.
So what we want to do is we want to queue a kernel mode APC. The kernel mode APC will only fire when we're running at less than APC level, effectively, in kernel. We do some tricks where we have these things called critical regions, but conceptually, when we're less than APC level in kernel, this thing will fire, right? And what it does is basically queue this user mode APC so that right about when we fully unwound our stack from your call into the kernel, it will fire, right? Because right when we're about to come back to user mode, it'll run this part of it, right? So the kernel mode APC is just required in order to queue this thing in and kick you out of a wait, because you could actually be in the kernel doing like an NT, or at the Win32 level, wait for single object, right? You could be waiting on an event, so effectively you are in the kernel. So the side effect of queuing the kernel APC is that it will kick you out of this wait and abort the wait.
Okay.
So you'll start unwinding, right? Because at some point you're in the kernel in this, NT wait for single object, KE, whatever, wait for object. And what happens is it will get aborted and start unwinding. And right when it's about to come back to user mode, you take this last thing and then you get blown away. Okay. So you don't leak any state that might be intermediately on your stack, like a temporary allocation or whatever it is, right?
And the same is true for wait for any, right?
Yes.
So just any of those waits.
Yeah, if you're doing like a user mode wait, you can get kicked out like this.
Okay.
Right. So the idea is there are certain cases where we've taken a kernel lock, right, and we're manipulating some kernel structure. So what we do is we basically block the kernel APCs before we take the lock, so that once we're in the lock or waiting on the lock, we don't get aborted from that wait.
Okay.
Now it's a little complicated, but maybe if you sit back and think about it a little bit, you'll see why we kind of need to do all this juggling.
Absolutely.
Yeah.
Because you don't want to leave any corrupt state in the kernel and the story.
Right, but then a side effect of this is that anytime we're going to take a kernel lock, we first need to raise to APC level, effectively. right? So we can block both these terminate APCs, and suspend is also implemented in the kernel APC. So there's a whole bunch of aspects here, but fundamentally the key is it needs to be done at this point so that we've unwound the kernel stack.
Absolutely.
And we freed everything up. Now the difference with kernel threads, system threads, is that there is no user mode. They never return to user mode. So how does this work? Well, you can't terminate a system thread from a different thread. It basically has to terminate itself when it's done. That's basically the design there.
Okay. Which makes sense.
Yeah.
That's good. I mean, it's good for stability and reliability of the system.
Yep.
I mean, very cool. Well, learned a lot here.
Yeah.
I mean, there's a lot goes on. I mean, it's good to talk about because there's so many issues with threading, right? Threading is one of the big burdens for programmers, especially dealing with asynchronous threads and the whole parallelism, parallelized code, and it's just hard to write concurrent code, et cetera, et cetera. So, really digging into what a thread is was very useful today.
Sure.
And how they work on the system is excellent. And some of the changes he made in Vista, which the process that doesn't require any threads is interesting, or the one that gives you a default execution context that you can't inject or suck out of,
right?
Which is interesting.
So that was one of the new things. We did other things like you improved the quota management, so you could say this user can only have this much working set or this much non-page pool or page pool or this kind of stuff. That's more for the government security regulations. Also, this thing can't use this much more than CPU, right? You as a user can't use more than 10% of the CPU. That's enforced now. We've done that. Create processes user, we moved that into kernel as part of all this stuff so that you can basically inherit handles from your parent when you create a process as a different user that didn't used to work in older releases. So things like this, incremental improvements, big underlying architectural changes. So
sure. All in the name of security, stability, and reliability, which is very important.
Yeah.
Right?
Yeah.
And performance.
Sure.
I mean, there's going to be implications on performance here.
Right.
So let's talk quickly, how long have you been working at Microsoft? Like, how long have you been working on this stuff?
So I've been at Microsoft for about 4 years.
Okay.
This specific stuff I've been working on for about the last 2 or so.
Okay.
But I've been working on the kernel for about 4 years here.
Cool.
So.
And what attracted you to kernel development?
I really like the low-level systems problems and the kind of stuff we have to think about here, the kind of synchronization, all these kind of issues of what code can run on top of what code, and kind of this whole mindset of once you go into the kernel, everything that as a user at a user level we think of applications, whatever. Going to kernel, it's all data structures, right? You can manipulate these things, like work out how these things work, and building the platform, really, right? Platform on which you can do all this stuff.
Excellent.
So I was into that always, so it seemed like a good place for me.
Good. Well, great job, man.
Yeah.
Looking forward to seeing how this manifests itself in Vista. I'm sure it'll be sort of light manifestation for those of us who spend much time in user mode.
Yeah.
But I still, it's cool that we talked about the complexity of terminating a thread and what happens. Because as a programmer, you just call APIs.
Right, and I think it was good that you touched on this fact that you can't really do it unless you
know what you're doing.
Now, the difference with terminate process is none of the threads are going to be running, right, anymore. So that's okay, right? When you blow away a process, we just incrementally terminate all of them and block creation of new threads in the process. Now that's okay because all of them are going away. You're not going to be in a state where you're hung or whatever, right?
Well, I mean, this explains perhaps why. Well, it does explain. So sometimes when you go into Task Manager and kill an application, it doesn't kill right away. Is that because of the cleanup that you're doing? So if I kill a process in Task Manager, say it's...
So, as I said, if the thing is waiting in kernel, right, it doesn't take necessarily that thing to back out, right? It's only if it's doing a user mode wait, right? And the process doesn't actually go away until all the threads have died from Task Manager. So even though you'll see this kind of ghost laying around maybe in Task Manager until all of them have run through this code path, right? And when the last thread goes away, we go into what's called process rundown,
which is where we, close all the handles in the process and delete the virtual address space, most of it. And then finally, the process object itself finally goes away when the last reference to it goes away. But effectively, it's dead when the last thread exits. It's different than object delete. It's kind of an important distinction.
True. Well, a thread isn't an object, right? Or is it?
Well, they are. Like when you do a create thread, you'll
Yes.
get back a handle. It's an object manager object. The eThread is an object manager object.
Got it.
Right.
Yep.
So the process handle is a handle to the process. So once the process has died, right, you can't create threads in it anymore, even though you still have a handle, right? So the process object still exists, so you can query some information about it. The ID remains, right?
Sure.
The ID only gets recycled when we finally delete the object.
Okay.
So stuff like this, right? There's a slight decoupling between the point at which the process dies and the point at which the object is no longer valid.
And so if I tried to create a thread in a process that's in the stage of dying,
It's not allowed.
It would throw an exception?
No, it just fails.
Just doesn't
It
work.
just
Get
says
an
process
E.
is terminating error.
Got it. Very cool. All right. Well, thank you for your time.
Sure.
It's been
Hopefully
good.
this was educational.
It definitely was. I mean, it's always fun to talk about threads and processes and whatnot, and really dig into how the system's working. I think
Okay.
it's important to get an idea and to meet the people who are making it happen. That's
Cool.
also number one. All right.
Thanks.
Thank you.